Hello and welcome back. In this lecture, we are going to continue our discussion on how to build convolutional neural networks. What we've done so far is made a single convolution filter that allows us to find in a given input image where the plus sign was. And the idea was that we should be able to convolve the given filter that is now being learned using a single training example with the input image and then do some post-processing that allows us to identify where that plus sign is. And remember, our main goal was to find where is Waldo, and that can be solved with a similar approach. We can perhaps have some training data, and we can learn where Waldo is using that particular filter. However, if you want to solve more generic tasks, such as classification, we need to do a bit better. But before moving on, let's just revisit what we did when we were trying to solve this particular problem. We had an input image and we had a corresponding target in our training set. So let me use my pen over here. So let's say we had an input image over here, and for the corresponding input image, we had a corresponding target in which we knew the locations of the objects of interest, which are indicated by these delta signs or these triangles over here. We wanted to learn the filter. We didn't know the filter that when convolved, so this is the convolution operator, with the input image and with some post-processing in the form of, let's say, sigmoid activation, yields an output image that when compared with the target should have the minimum amount of error, or in other words, the output of this convolution of the input with the filter that we want to learn should match what the target is, right? And the difference between the two is called error, and we can use that error to update the filter because that is not known to us. So the representation of this machine learning problem can be very simple. We have an input image, we convolve it with a given filter, we apply some activation on top of it, which I indicate by this sigma, or if you want to do sigmoid activation, and that gives us an output image that I'm going to call y. Now for a given y, we want to compare it to a given our given target, which is t, and let's say we can use the square of that as the error signal. Once we get that error signal, what we want to do is to simply take this error, and we want to take the derivative of this with respect to the filter weights, and we can use this signal to update our filter weights. That's the process that we did, and we can use the same process and to build even more complex detection or classification models, and that's what we are going to discuss next. We know that we can achieve classification when you have a multi-layer perceptron. So you feed all your input features, let's say for a given example, and those are then passed on to the next hidden layer and the next hidden layer until an output is produced. For a given input example, we know what the target is, and we can use the difference between the output and the target again here, which is called loss or an error, and we can use that to update each of these weights that we have in this neural network, and we can achieve classification. So let's say if you want to do image classification, for example, if an input image contains 8, your output should be that it contains an image 8 in it. If there is a 7 in it, let's say you want to produce 7, and so on. So one way we can do that is to simply flatten this output and then feed that as an input to this multi-layer perceptron. But there are a few problems with that. The first problem is that we can have images in which you can have 8 on the side, you can have 8 over here. So sorry, these two images should be the same size, so below that let's say there can be 8 here, and if you feed those as input into the image, because the object is not localized, these multi-layer perceptrons will not be able to do very well. So there is that problem. There can be different scales of 8, so there can be a small 8 and then there can be a very large 8, so we can have that problem in there as well. What we want is a generic method that allows us to extract features and then pass those features onto this multi-layer perceptron, so that the multi-layer perceptron can classify whether there is an 8 in there, whether there is a 7 in there, or whether there is Waldo in there. So that's what we want to do using these multi-layer perceptrons. The other problem with feeding this direct input or a flattened version of it is that the dimensionality of the input is going to be very large. So let's say if this image is 256 by 256 pixels, if we flatten it, it's going to be a huge vector of input. And then because the multi-layer perceptron is a dense network, will not be able to do very well because of the number of weights and the computation burden it's going to introduce. However, if we do this, that is what we did earlier. We have a convolution filter learning method. I'm gonna just call it CF, and then we have a multi-layer perceptron. If we connect these two so that an input image is given as input, and what happens is that, let's say for an input image, we know where the object of interest is in that image. We first use that information, and then what we try to do is try to learn the filter so that we learn to detect that particular object. And then what we do is we flatten this target vector, this output vector. So we flatten it into a single vector, and then we feed that as an input to the next one to say what type of object it is, right? So we can have we can take these two ideas that we had of detection using convolution filters, in which the objective is to learn filters, and then we can have a multi-layer perceptron that can achieve classification. Now there are problems with this approach as well, because the output that you are going to, first of all, there are two problems here in the convolution filter part. The first problem is you need to localize where the target is, right? And for a given classification problem, it is actually easier to simply label the object that this contains an 8 or this image contains a 7, rather than trying to localize where that object is. That is more annotation burden or more labeling burden. So typically we know the class of an image, whether it contains Waldo or not, rather than trying to understand where Waldo is and label that as a location, right? So there's an annotation problem with that, and so we only have a target at the output, the class target at the output, not object detection target that should be available for us in order to learn that filter, right? Because this convolution filter learning part requires the knowledge of where that particular target is. So we don't know that. The only thing we know is, for a given example, which is an image, we know what the target label is. So that's one of the problems. We can overcome that problem by simply feeding this output of this thing that it produces into this input of the multi-layer perceptron by flattening it, and then using this error signal to update not only these weights but also the weights of this filter, or updating this filter. Sorry for the horrible line, but I hope you get the idea. The error signal that we can get, if we combine these two networks, you feed an input image, it goes through the convolution filters first, produces an output, which is then flattened, and then we feed it, the flattened output, to the input layer, right? And then that produces an output where we can compare it with a known target and compute a loss, which is then fed back to learn both the weights of this MLP as well as the filters in the convolution filter part. So that's how this can be resolved, but there is still a problem. And that problem is this output is still very large in size. If our goal is just to classify, what we can do then is if we use this dimensionality, this can be, let's say, 256 by 256 dimensional. And if you flatten this, it's still going to result in a very large input dimension for this multi-layer perceptron part. So somehow we need to reduce this output size so that we are still able to classify, but we don't lose any relevant information. This was the idea behind the birth of convolutional neural networks. If we can reduce this output size somehow, we should be able to combine the two, multi-layer perceptron, which are universal approximators, and object detections using convolution filters, into the same network, which will be called convolutional neural networks. And the way we achieve that is first of all, we want to we can reduce the size of the output of the convolution filter part through either pooling, I'm going to explain what that is, or by striding, which we've already talked about. When we convolve a given input image with another input image, with a filter, if you have an input image that is shown over here and you have a filter size of size 3 by 3, you can, in convolution, choose to move by a step of 1, which would be called a stride of 1, and then output image is going to be, for this particular case, of size 5 by 5. So if you've got a 7 by 7 input image, a 3 by 3 filter, the output with a stride of 1 is going to be an image of size 5 by 5. However, if you use a stride of 3, then the output image that you're going to get as a consequence of convolution is going to be smaller. In this case, it's going to be 2 by 2. Try to wrap your head around this, that stride changes the size of the output, right? The other way we can do, for a fixed stride, what we can do is we can try to do pooling. So once we get the output for a given convolution, we can take the maximum value of that image. Let's say if you got this input image over here, the output image of convolution over here. So this is the convolution output over here. And what we can do is we can take the maximum value within each 2 by 2 neighborhood or 3 by 3 neighborhood, and we can, let's say if we apply that as a pooling method, then what we have over here within these four numbers, 20 is the largest number, so we replace that over there. Out of these four, 30 is the largest number, so we put that over here. Or we can do averaging as well. What we can do is take an average of this, and then that average is going to come to 13. But notice that we have been able to reduce the size of this output into a much smaller size, which can then be fed into the multilayer perceptron portion of our convolution neural network. Now, it requires some deeper thinking on what stride should I choose. If your objects are really small, should I choose a large stride or a small stride? Again, if my object of interest is really small, should I choose a large pooling size, or what should I be using pooling, or what sort of pooling should I be using in that case? So it depends upon the size of the object, that depends upon the problem that you're trying to solve, but this can be a generic way of reducing a large image from the output of the convolution to a smaller size, a smaller output that can then be fed into the convolution neural network, or the multilayer perceptron portion of the convolution neural network. So if you think about the convolution neural network, a very simple one, it would have two parts. And you can break down any convolution neural networks into these two parts. The first part acts as a detector, and the second part acts as a classifier. What happens is once you give an input image, it is convolved with a filter. It is post-processed with an activation function. So this indicates convolution over here, and this indicates the application of an activation function. That output, which is we are now calling a feature map, is pooled. That is, either we can use, for example, maximum pooling, or we can use average pooling, and then that pooled version is flattened, and then that flattened version is fed into the classifier bit that generates a prediction label now, rather than generating an image. And that prediction label is then compared to a target, and a loss is computed. Now this loss is going to be used to modify the weights of this classifier part, or the multilayer perceptron part, or the dense part of the network, as well as the filters that you have over here. So let's say if you want to classify a given input image, which contains, whether it contains an 8 or not, that input image is passed on through a filter. We generate a feature map which is pooled, it is flattened, and once that has been done, we give it to our convolution, the classifier bit of our convolution neural network, which now generates a label. Let's say that if the true label does not match the target label, we have a loss, which is then fed back, and those weights of both the network, of the classified network, as well as the filter are updated until we match the output. So this is the most basic convolution neural network for machine learning that you can use. And these principles hold even if you want to use a very big neural network. So if your objective is just to find Waldo or not, in this case, your training images are going to look like this, or your training data is going to look like this. You have an input image and you have got a corresponding label of whether Waldo is in there or not. You don't need to localize Waldo or tell the network where Waldo is in that image. So if you have such data, these networks would then allow you to use such data to update their weights, so that you feed an input image and it would generate an output that can be used to classify these input images. Okay. You can use, instead of using a single filter, you can use banks of filter. That is, instead, like over here, we had a single filter, right? You can have multiple filters, each of one of them performing convolution, and then that means is that it's going to produce multiple feature maps, each of the which can be pooled, and then you can flatten all of them and then feed that into the classifier. So you can have all different types of variants. You can also use a deeper version of this classifier part, so you can have multiple layers of neurons in your classifier portion. And then that is what is called a convolution neural network. So a convolution neural network uses a fully connected multilayer perceptron structure or dense network to classify images, but it also uses convolution filters that, or multiple convolution filters that essentially allow you to detect objects or detect various type of features. That's one way to look at it. Another way to look at it is that the first portion, the detector portion, identifies important features from the input image, produces that as an output, which is then given to your classifier, which produces an output. So that's how this works. These were originally proposed even actually in I think it was in the 90s that people came up with this structure, Jan Lee Kun and his team. So let's say if you want to do object classification or letter classification, you get an input image, you convolve it with multiple filters. In this case, if you have 6 filters, you can get 6 different outputs. So the first filter convolved with the input produces a single output, which we call a feature map. You can have 6 of these, or this particular network had 6 of these, and then those can actually be fed into another layer of filters. So you can have filters on top of filters, or filters operating on the top on filter outputs from other filters, right? And you can have, let's say if there are 6 filters over here, you can produce more outputs, and then those can be flattened, all of them, and given to a fully connected layer, which then produces an output. So let's say if you want to do digit classification, your input image is going to contain a single image, a single digit. You pass it through multiple filters. At the output layer, you would have then 10 neurons to classify what the input digit is. If the first neuron fires, you have a single, your digit is 1. If it is 2, or so on, you can have digit classification using such a structure. At the core of it, there are 2 parts: the convolution filter portion, or the detector portion as I'm calling it, and the classification bit. The classification bit is pretty much the same as we had discussed in terms of multilayer perceptrons. Yes, it can have multiple layers, but the input for that is the output of your detector portion. Now, the detector is composed of multiple convolutions, and the good thing about convolution is that it is invariant. The way it's implemented here is that it's invariant to translations. So it doesn't matter where that particular object is. If that object moves to another location, we should still be able to detect that and then classify it at the output. Okay, so that's the overall goal. And if you think about it a bit more, you have sort of a hierarchy. So you can have features that produce, you can have primitive features. If, for example, you want to detect what a car is, you can have different features that detect the horizontal lines and vertical lines or diagonal lines first, which then go up into making the body of the car. That can also be detected using a filter. And then you can have a sort of you can have you can pool that, you can have you can flatten it, which is then, and these features are then used for classification. So the way I think about these convolution neural networks is that the detector portion automatically extract features which are then used for classification. Okay, so this is an implementation of a very simple convolution neural network in PyTorch, and we're going to go through the code next, but it's important for you to understand what the structure of the convolution neural network is. The intelligent thing here is that we can learn both the filters and the weights of the classification network using a single label at the output. So all your images have to be is, you need to have an image with a corresponding class label, and then you'll be able to use that information to learn both the structure of the filters that you have as well as weights of your multilayer perceptron. Thank you.